I will get started. Let me begin with a word of prayer. So, Heavenly Father, we thank you for this day, and I thank you for this class and this time we have to meet together. Help us to glorify you what we do and just understand a little bit more about your creation today, Lord. In your name I pray, Lord Jesus. Amen. Lest I forget, here's the... I'm trying to... I got the top hat code over there, and I've got this exciting attendance sheet over here, so that's why I'll make sure I count you attended if you're here. If you're not here, don't mark the sheet. So, I think I have all your homeworks, and, oh, no, I do. And so I was a little bit kind of saddened that I didn't have an example where, like our strong induction examples that I gave you guys from the book and everything, it seemed like they at most involved like the, maybe two steps, right? Like it's involved n and n minus 1. That was kind of enough to weave it all together. Maybe that one about the integer linear combination of the two integers, that one was a little bit more, perhaps a little bit more nuanced. But there are examples where you have to use like the full strength of strong induction, right? Like it's necessary to use steps 1 all the way up through n in order to prove something is true. And I was a little bit relieved, but also a little bit annoyed that I hadn't noticed that problem 47b is exactly such a problem. At least I think, anyway. Thank you. So I think 47b, at least with my current understanding of it, it seems like I need strong induction to solve the thing. All right, so I'm sure much partial credit will be given for that problem. Another thing is, I didn't get any questions from you guys. 47b, as it's stated, is not correct, right? Because if you look at it, we could have a sub k equals to 0, and that would trivially satisfy the defining relation for the summation there. So really, for that problem to have the solution necessarily a sub k is equal to k, we do need to assume that we're talking about non-zero coefficients. Otherwise, there are two solutions. There's either the 0 solution or the one you were asked to prove. But anyway, so there's that. But I do think that was almost certainly the most hard problem in the homework, I think. Yeah?
What constitutes like needing to do strong induction?
Strong induction, I would say it's not enough like to assume that n is true. You also need knowledge of things before n in order to establish n plus 1. So like that's the difference in my book between a proof which is necessitating strong induction versus not. I mean, we can always trivially do strong induction on every single one by assuming, you know, that we know 1 up to n, and then usually n plus 1. Like if the details of the proof just allow for n to imply n plus 1, well then you didn't really even use all of the, you know, the strong inductive hypothesis. But those problems, like I said, typically occur in recurrence relations, and there's a smattering of other places like I think the proper proof of the prime factorization of integers uses strong induction. Dr. Schmidt was telling me, talking to him yesterday, and there are other places. I mean, strong induction has a place. Okay, so that was one thing. The other thing I should tell you guys is there's an example I've been meaning to share with you, and I just keep missing it. And so we'll be, most of today we'll spend talking about equivalence relations, all right? But I have one more, for the moment, induction example to share with you. And this is an example of a false proof. So your job, your mission, should you choose to accept it, is to tell me where I'm wrong, all right? So here's the claim. All horses have the same color. Let me rephrase that. We could say every set of n horses has the same color. All right. And so the universe of this discourse is monochromatic horses, all right? I don't allow for horses that have like spots or something, all right? So all courses that have just one color have the same color. So here's how the proof goes. N equals to 1. You've got one horse, right? And so it has one color, right? That seems pretty clear. So suppose it's true. Claim true for any set of n horses. All right, that's our induction hypothesis. Consider n plus 1 horses, right? So I won't try to draw a picture, but I'll just illustrate them like this. 1, 2, 3, dot, 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 n plus 1, right? You guys with me? All right. So by the induction hypothesis, we can look then, this right here is a set of n horses, right? How did F become? Why is there an F there? What's wrong with me? Horses. On the flip side, if we just look at the last n of them, this is n horses, right? By the induction hypothesis, the first set of n horses and the last set of n horses has the same color, right? That's the induction claim. But the horses which are in the intersection of these two sets have just one color, right? Therefore, the color of the first n and the color of the last n must be the same. Therefore, n plus 1 horses have the same color. Right? Therefore, by proof by mathematical induction, all horses have the same color. This is obviously false. Where am I wrong? What's the flaw in the argument? This illustrates something that has to be true about our induction arguments, is that n has to imply n plus 1 for any n greater than or equal to 1. Right? Is this okay for n equals to 2? If I've got 2 horses and I add a third one, right? What's that look like? 1, 2, 3, right? So I've got the first and the last, right? And if I have n equals to 3, and I look at n plus 1 being 4, I've got 2 that are in the intersection, right? What about n equals to 1? What about n equals to 1? I've got my first horse, my n plus 1 horse is my second horse, right? Here's the first, oh man, here's the first n horses, right? Here's the last n horses. My argument about the intersection of the first and the last n horses is specious in this case, right? It's bogus. To quote my community college professor, this dog does not hunt. There is no intersection at that base case. So I've let about a half a dozen different students marinate in this for about like 5 to 10 minutes. Usually people can't figure it out. Not right away anyway. It takes a while for people to kind of go, oh. So first of all, you have to understand the false proof, right? That's the first step. I hope I've done that much for you today. But to unravel the error, there's some errors are really kind of insidious, Because it's very believable, I think, at least at first glance, that you look at the first n and you look at the last n, there should be some intersection, right? Except when there's not, right? When n equals 1, the first and the last n of n plus 1, there's no overlap. That's where the argument fails. Okay, anyway, that's it about that. This is the probably the most famous false proof using induction, like false induction proof. There's a billion different variations of this thing. If you go look, and you'll find them, you know. All right, so let us go on. So section 5.2 in my notes, equivalence relations. Any questions? All right. So here's our definition. And this is probably one of the top 10 most important definitions in this course, I would say. Here goes. Let A be a set. All right. And R a relation on A, period. We say R is an equivalence relation all right, if R is, number one, reflexive, number two, symmetric, and number three, transitive. All right, so I should explain what those words mean in this context, right? So reflexive means that for each x in A, x is related to x. Symmetric means, if x and y are in A and x relates to y, then y relates to x. Transitive means if x, y, and z are in A and x is related to y and y is related to z, then what? X is related to z, right? So, comment I should make right away is we don't always use R for the equivalence relation. Like I think I started doing this last time even. Sometimes we use like a squiggle or some other symbol to indicate the equivalence, right? So let me just make a remark. If x, r, y is denoted x squiggle y, then 1 becomes what? X is related to x. 2 becomes x is related to y, implies y is related to x. 3 becomes x related to y, and y related to z implies x is related to z. Right? Again, that has to hold for all x in A. That has to hold for all x and y in A. And that has to hold for all, x, y, and z in A. What's the fine print contained in the statement that x is a relation on A? What did that mean for us last time? Do you guys remember? Could we have let me put it a different way. Could we have a relation from A to B? Or let's say, could we have a relation from A to A, which was not a relation on A? I believe the answer is yes, because say relation on A, we presuppose that the domain of the relation was what? A itself, right? So this is in the first definition in chapter 5, all right? All right, so example. So does this remind you of anything? How about this? Let S be any non-empty set, and let X and Y be an S, then X related to Y, if and only if X equals to Y. All right? My claim is that that defines an equivalence relation, right? So check it out, right? X is equal to X for all X and S, right? That's a part of what we mean by equality, right? Notice that if X and Y are in S and X is equal to Y, that implies that Y is equal to X, right? So thus XRY implies YRX, for all X and Y in S, thus that is R is symmetric. There's an error in the notes. In the notes I've copy pasted X equals to Y twice. On my example 5.23, I meant to put Y equals to X. Otherwise, it doesn't seem like I'm saying anything, and indeed I'm not. There's a typo in the notes right there. Nothing really terribly profound going on in this example. And finally, if we have X, Y, and Z in S, and X is related to Y, and Y is related to Z, then what? We have got X is equal to Y, and we've got Y is equal to Z. Thus what? X equals to Y equals to Z. Therefore, X is related to Z. So R is transitive. All right? In short, equality is an equivalence relation. All right? Equality, as we commonly understand it, is equivalence. What do we mean by equality, though? What does that even mean? We say two elements are equal. What are we saying? You ever think about this? What does it mean to say X is equal to 3? Dr. Scambortis put this on a test, I think in Calculus 2 or something, many years ago, just to see what would happen. He's like, X is equal to 5. What can you say about X? And like two-thirds of the class left it blank. They were completely snowed over by this question. But the answer was, X is equal to 5. That's what you can say. It means X is the number 5, right? So when we say X is equal to 3, it means X is the number 3. And apparently we mean that without any kind of nuance, let's say any, right? So example 2. So equivalence, the idea of equivalence relation is to abstract the notion of equality. And so we're going to broaden our concept of sameness, all right, in different examples. And so here's one. We can let the set that we're going to find the equivalence relation on, which I guess I've been using, this set is what I've been calling A in the definition. So let's say A is a subset of, oh, wait a minute. Let me just stick with my, sorry guys, give me a second here. Define equivalence relation on S, which is going to be a subset of Z cross Z. All right. And what is this S? This S is going to be pairs, A comma B, such that A and B are integers, and B is not equal to 0, okay? That's the set. We're going to define an equivalence relation on this set. All right? And the way we're going to do that, we're going to use the squiggle notation this time. So definition, we'll say that AB is equivalent to CD, all right? If and only if. So this is my definition of equivalence. Let me show you the man behind the curtain here before I even write down the definition. What we're doing right now, guys, is we're trying to look at a formal model of fractions. That's the whole idea of this example. So here, this A comma B is like a model for the fraction A over B, all right? So if I want to say two fractions are equal, right? If I had, C over D, CD models C over D, all right? If you like, it represents it. What should we want about these pairs? How should we define this equivalence? If we have equality of the fractions, how would that be judged? How would you judge two fractions are equal? Ever think about this? Yeah.
A is a multiple of C and B is the same multiple of D.
A is a multiple of C and B is the same multiple of D. That's one way you could do it, but that would be more laborious. I mean, you're not wrong. Let me see if I can make that. Let me see if I can translate what you said into what I'm about to write. So you're like A is equal to, say, K times C, and B is also equal to K times D, right? That would be what you said. So, and K apparently is equal to, yeah, I don't know. A over C. See, I don't want to say that because I don't know C is non-zero. C could be 0. I think you're right, but I don't know how to get from there to what I want to write. So our definition, that's a good idea. I'll have to think more about how to get from there to what I'm about to write. But what we want to say is just AD is equal to BC, right? If that's the case, then that forces equality of these two fractions, right? And of course, if we did your, so AD would be equal to, for you, KCD, right? Which would be equal to, let's see here, CKD, which would equal to CB. So you see, you can get my criteria from your criteria if you want. But you see, the advantage of the definition I just wrote is that we don't have to introduce yet another, integer to. But you're right. In fact, that's how I think about it in terms of arithmetic, right? Like, 5/10 is equal to 1/2, right? Because I've got like 5 times 1 and 5 times 2, and the 5s, they be canceling, and it leaves me a half, right? I mean, fair enough. But this is the definition we're going to work with. Now the question is, so this right here, all this stuff over here, guys, is not part of the problem. This is just, I'm telling you, this is the backstory of this example, all right? So I shouldn't have really told you. Traditionally, we don't tell you this until the end of the example, but I decided to tell you at the start. I don't know. Maybe it was a bad idea. Maybe I should have just stuck with this. So then, if that's our definition of the equivalence relation, can we check that it's reflexive? What do we do? Let, AB get, oh no, excuse me, element of S. Then AB equivalent to AB if and only if what? So here we have to understand what we're doing, right? This has C equals to A and D equals to B, right? So this would become AB is equal to BA, which is true, since multiplication in the integers commutes, right? Thus, therefore, squiggle is reflexive, right? So that's number one. Number two, suppose that we have, A, B, C, D in S, and AB is equivalent to CD, right? Then, by definition, we have AD is equal to BC, which implies what? I can write the equality the other way, right? BC is equal to AD, right? Which tells me what, by definition? This tells me that CD is equivalent to AB. Because we say that the pairs are equivalent if the first times the last is equal to the second times the next to last in the reading this, right? So first, I think I need to, I'm not quite there yet, am I? Let me draw a pattern here. See, I'm not quite giving you a good faith argument yet, am I? Let's think through this a little more carefully. So this A goes with the last one, right? The B goes with here, right? So AD and, well, I should probably use some color coding here. So you guys tell me, is my pattern quite right to make my conclusion yet? I don't think it is. I think the pattern needs to be a little bit different. So, all right. I mean, this is true. That's given. That's true because equality is reflexive, right? I mean, symmetric. And all right. So, so this would be. I think I need to do one more step. I think I need to go. CB is equal to DA, right? Maybe. Would that do it? Because then if we match the pattern,
I think it's CB equals AD.
I should leave the AD alone? I was about to check, but, all right, so you think it's that. Let's see if that's right. So, you got to work backwards, right? AD, CB, so that's my, so this tells me the first and the last, and the other one tells me the middle one. No, I think I needed to flip both because see here the gotta find the words. So here BC. B goes here, C goes there, right? So if I have AD, that would put A here and D there, I think. But what I wanted was DA. I think I want DA there. Because that would put, according to our definition up here, B is in the D spot, right? So that puts the D here, and A is in the, rather A is in the C spot, so that puts the C here, puts the A here. Anyway, so I think I have demonstrated that it would be wise to introduce another set of 4 letters to establish the pattern and then make substitutions to show that the pattern holds. That would be like a better way to organize this proof because I'm having to think too hard about the pattern matching for sure, you know. But anyway, but there it is. So therefore, is symmetric. Right? Let's see here. See if I can put into practice what I was just mumbling about. So, all right. Let's use, so we had, so run us to the definition. AB equivalent to CD if and only if what? AD equals to BC, right? Yeah? All right, so let's assume that XY is related to YZ and YZ is related to UW. All right. So this tells me what? This tells us that X times Z is equal to wait, what? I'm sorry, guys. I can't put the same letter in both of those. What's wrong with me? Good night. I was like, y squared. Wait, what? No. Okay, so I'm supposed to use, I should use distinct letters for these pairs, right? X, Y, and what should I put here? Not Y, Z, but ZW. All right? All right. And over here, we should have like ZW equivalent to, I need another letters, right? X, Y, ZW, alpha, beta. There we go. Okay. So this then gives us what? This gives us X times W is equal to Y times Z. This tells us what? Z times beta is equal to W times alpha. All right? According to my definition. So then what? What's our goal? We seek to show what? That XY is related to what? Alpha beta, right? That would show transitivity here. And so this is equivalent to what? This we need what? We need X times beta, right? Is equal to Y times alpha. How should we go about this? What do you think? Can you tell me anything in particular about, like, all of these pairs are from S, right? That's our assumption. You know, probably should mention that at some point that's going to be necessary, you know. What does that say? That means that all of these are integers, right? But also, what's non-zero? Y, W, and beta are not equal to 0, right? Any ideas? What should we do here? All right, you say, notice Z is equal to W alpha over beta. Since beta is not equal to 0, thus what?
Plug it in the first place.
XW is equal to Y Z, which is equal to Y times W alpha over beta. All right, very good. Then what are we going to do?
Y's cancel.
The Y's, well, I suppose they do, but I don't think that helps us. Because we're trying to get to X beta equal to Y alpha. And you don't want to cancel that. That Y is mission critical. But this was an excellent idea, and you're almost there. Just ignore my YZ. Ignore it. Right? Instead, cancel the W's. Right? So this implies that XW over W is equal to Y W alpha over W beta, as W is not equal to 0. Right? But the W's, they do canceling. So that gives us an X is equal to, apparently, Y alpha over beta, which then tells me that X beta is equal to Y alpha. So your idea was excellent. It's exactly what we needed to do. Because now, therefore what? XY is equivalent to alpha beta. So if you get stuck on a proof like this, if it's something that is, so this is a formalization of fractions, right? So here's just a pro tip for you. If you get stuck on this kind of proof, one of the things you can do is go back to like what this is modeling, and you can kind of cheat using the arithmetic you already know. Like for this one, we are trying to show, let me see if there's another way I can explain. Like this is good. This is perfectly good solution. Another way to attack it is you're trying to get your pause on, where is it? We're trying to get to, sorry, I lost track of all these letters here. Essentially, this is showing X over Y is equal to alpha over beta, right? And so we're let me write it in a different color here. So we're given in the usual fraction notation that X over Y is equal to Z over W, right? And also that Z over W is equal to alpha over beta, right? So, you can, I mean, in this notation, the whole thing becomes stupid, right? But if we, most instructors would be very annoyed if you gave the solution like that, me included. I would, if I was to give this problem on a test, I would be careful to say something like, your proof will not include fractions. See, that would be very annoying, but it would force you to think about the thing I wanted you to think about. But this becomes XW equals to YZ, and this one gives us what? Z beta equals to W alpha. And man, I don't know. I guess we just have to do what you did. But anyway, I guess I have nothing more to say here. There may be a better proof in the notes, which I'm not looking at the moment, but I'm just going to erase this because it's true, but it's not really the way we should think about this particular. This is why I have mixed feelings about this example, because in some sense it's too close to something that you just take for granted for you to appreciate properly. But if you take another view of this, I'm telling you how we can define fractions carefully. This gives us a way of understanding why it is that 1/2 is 5/10, is 3/6, is 4/8, is 100 over 200. These are all just different representatives of the same fraction 1/2. All right. So we need to move on here. I'm starting to talk about the next concept here. All right. So we should talk about equivalence class. So, here's something to think about. If you go back to last class and you look at the different relations that we had, the question you can ask is, are any of those equivalence relations? And to answer that question, it might be a little bit hard to see, but it will become very easy once we get like the next idea in front of us. We're not quite there, but we'll get there here. So definition, let S be a set with equivalence relation R. The equivalence class containing X and S, all right, is a set defined as follows. So bracket X with a sub R on it, and here it is. It's Y and S such that X is related to Y. And so we also say that S mod R is the set of equivalence classes. Right? And if there's no danger confusion, we drop the R and use X sub R just equals to X. In fact, there are a few other notations which are sometimes used that are particular to a particular context of this idea. But just as a sort of generic notation for this course, we'll use brackets. Bracket sub R to denote the equivalence class containing X. So, okay, so like with this notation, a particular use of this would be to talk about rational numbers, right? Like rational numbers. So example 3, if I take my previous equivalence relation, and I take that set S and I mod by the equivalence relation that's called. We could also write like this. If the R is denoted by a squiggle, we could write like R divided by squiggle to denote the set of equivalence classes. This would be, like the equivalence class of AB such that AB is an element of S from the previous example. Right. So, for example, if I was to say, what's the equivalence class with 1, 2, right? Well, that's got all kinds of things in it. It's got 1, 2, of course, but it's also got like 5/10, or as I was saying, 100 over 200, etc. Right? 3/6. I mean, you name it. That infinite set of pairs, every one of those pairs represents the fraction 1/2. So you can see that you can use this to essentially give a definition for the rational numbers. We could define the rational numbers as sets of pairs which are judged equivalent, right, by this equivalence relation. Yeah. And I should probably put some scare quotes on this equals, because perhaps you could define the rational numbers differently, but this is one quote-unquote model of the rational numbers. One way you could construct the rational numbers from pairs of integers where the second integer is non-zero. All right, let's look at a simpler equivalence relation. This has been with us since nearly the beginning of the course. Even numbers and odd numbers, all right? So, and by the way, point of order here, I think I just changed the set that we're finding the equivalence relation on from S. I had A in the definition, but now I'm talking about S, so don't let that confuse you. If you want to, you can go back and put S here instead of A. I mean, if I was to edit the notes again, I'd probably do that. I didn't notice that I changed the letter of the set here, going from one thing to another. We don't have a privileged notation for this, right? So it's the concept, not the letter, that matters, but anyway. Okay, so example 4. We'll take the set to be the integers, all right, and we'll say let x and y be integers, right? Then define x related to y if and only if x minus y is even. All right. Is this an equivalence relation? So number 1, x minus x is equal to 0, which is even, right? Because that's, 0 times 2. Well, anyway, let me just say 0 is even. Therefore, x is related to x for each integer, right? So this is reflexive. 2, if x minus y is equal to 2k for some k and z, then what? Y minus x, right, is equal to 2 times minus k, right? For minus k, an integer, right? So therefore, x related to y implies y related to x for all x and y and z, right? Because we see that if the difference is even, then minus the difference is also even. And so it's symmetric. 3, if we have x related to y and y is related to z, then there exists, let's say, j and k in the integers such that what? X minus y is equal to 2j and y minus z is equal to 2k. Thus what? Let's see here. So we've got x minus z is equal to, so what do we want to do here? How about this? We want to make a y appear, but there's no y. How can we make a y appear? What's the trick? Because we know about x minus y, we know about y minus z, right? So what should I do? Because I want to show that x minus z is a multiple of 2, right? Well, I know about x minus y, right? if I do that, to be fair, what do I have to do? There was no minus y to start with, yeah?
Just plus y minus z.
Yeah, plus y minus z. And that's, why is that allowed? Because I've just done what? I've just added 0, right? There's a way of reformulating the transitivity proof we went through earlier as multiplication by 1, if I had been more conniving today. But, you know, you can almost always make proofs about multiplying by 1 or adding 0 if they're these kind of things. But, yeah, so we just added 0. But this is equal to what? This is equal to, by assumption, 2j plus what? 2k, which also known as 2 times j plus k, where j plus k is a integer, right? So thus, hence, x minus z is even, and we find that x is related to z. So, in summary, hence, R is an equivalence relation. Why? Because we have shown it is symmetric, it's reflexive, it's symmetric, and it's transitive. This is what we must show to prove something's an equivalence relation. All right? So then what? We can ask, so now we have this new idea about equivalence class. What's the equivalence class here? Like we can write it out, yeah? I'm going to put it up here. What's the equivalence class containing, you pick a number, any number, I don't care. What's the equivalence class containing 1, let's say? What would that be? We're talking about x in the integers, such that what? X is what? Definition, x related to, my bad, I'm supposed to do y. Let me y in the integers such that what? 1 is related to y. What does that mean here? We're talking about y in the integers such that 1 minus y is equal to 2k for some k in the integers, right? That's what it means. That's the definition of the equivalence, that the difference is is even, right? It's a multiple of 2 in this case. So what's that tell me? Y is equal to what? I've spranoed the board. Let's see here. Y in z such that what? Y is equal to 1 minus 2k, right? Or perhaps I could write it a little bit more like just in your face. This is y in the integers such that y is equal to 2 times minus k plus 1, right? What are we talking about? What is that set? Yeah. Yeah, these are just odd numbers. So the equivalence class containing 1 is the set of odd integers. So, and I think I have a notation which is kind of funny. Set of odd integers. If you like, you could also use this notation. It is 1 plus 2z. That's a notation I haven't used much yet, but we could use this notation. It's really 1 plus twice the set of integers. Right? What's the equivalence class here containing 0? So we're talking about y in the integers such that, 0 is related to y. And I'm going to trade that for y in the integers such that y is related to 0, because I can do it. It's symmetric, right? And so there we're talking about y in the integers such that there exists j in the integers with y minus 0 equals to 2j, right? In other words, we're looking at 2j such that j is an integer. Just getting to the point here. So what we're talking about is the set of twice the integers. In other words, the equivalence class containing 0 is precisely the even numbers, which I have. Well, I have one notation when you can have 3. I think I have, like, in the notes something like this: E for even, O for odd. So here's something you've probably never done before. Have you ever thought about how to add sets and multiply sets? Like, how would you do that? If I had two sets, like S and T, what would I mean by S plus T? What do you think that would mean? How would we define the addition of two sets if we could? I suppose that's something we never defined with our set. We talked about unions, intersections, Cartesian products and such, but I don't think we ever defined what would S plus T mean. Here's what I would mean by that. I would mean X plus Y, such that X is in S and Y is in T. So it's just the set of sums like that. And what would I mean by like a product of two sets? So I would mean XY, such that X is in S and Y is in T. That's what I would mean by like the addition and the multiplication of two sets, right? So we can look at this. What happens if I take like the set containing 0, the equivalence class containing 0, the equivalence class containing 0? What does that equal to? And on the other hand, what would be the like equivalence class containing 0 plus the equivalence class containing 1 equal to? And what would the equivalence class contain? What would this look like? I don't want to prove it. Let's just think through it, okay, guys? What happens if you add even numbers together? You get another even number, right? So this, again, gives us 0. If I take an even plus an odd, I get odd, right? You know how to prove it. So, yeah. And by the way, if I take an odd plus an even, still get odd, right? The addition is commutative here. What's odd plus odd? Even, right. So if we think of the integers, all right, mod this equivalence relation that I'm just talking about, right? There are only two things in here, the even numbers and the odd numbers. The equivalence, the set of equivalence classes of this equivalence relation only has two equivalence classes, the even numbers and the odd numbers. And in fact, we can understand an arithmetic on these. Right? I can draw like little tables to indicate how they add. If I'm adding these, how it goes. And if I'm multiplying these, how does it go? Multiplication's kind of a little bit, I didn't talk about that yet, but what happens if we take like even times odd, or odd times even, or even times even, or odd times odd? How those work out. Think about that. What's the product? Product of even and odd, even. Product of odd and even, even. Product of even and even, even. So the first three cases here, they'd be 0. And odd times odd is odd. I feel like that.